Hello friends, this video on structure of atom part 33 is brought to you by examfear.com. No more fear from exam. Before watching the video, please make sure that you have watched part 1 to part 32. Let's understand the energies of orbital for hydrogen. Please note it's only for hydrogen. So here in hydrogen, the energy is determined only by principal quantum number. So 1s will have lesser energy, all 2s in p will have equal energy, all 3s pd will have same energy, 4s pdf will have same energy, but 4 will be more than 3, 3 will be more than 2 and much like this. This is only for hydrogen, not for the multi-electron atom. Orbitals having same energy are called degenerate cells. They are called degenerate cell. The 1s in the hydrogen atom is the most stable condition and it's called ground state, right? And the electrons in this orbital are strongly held by nucleus. They have minimum energy. Electrons in 2s, 2p and higher orbitals are called excited state because they are not in ground state, they are excited state and they have lesser energy. It's easy to pluck the electrons out of the excited state orbitals. And the only electrical interaction between the hydrogen atoms is between the negatively charged electron and nucleus. That's the only electrical interaction, the positive nucleus and the negative electron. So for a multi-electron atom, the energies, if you see, that does not depend on n always, that depends on L also, that is n plus L defines the energy of the multi-electron atom, right? And the main reason is the mutual repulsion which gets among the electrons in the multi-electron atom. That's the reason why the L also comes into picture, right? So the stability of the electron in the multi-electron atom is because the total attractive interaction, okay, that is more than the repulsive interaction, because there are so many electrons and there are repulsive attraction between electrons also in the multi-electron atoms, and there is a positive nucleus, there is an attraction also here, there is a repulsion also here. So all this force combined and the attraction is more than repulsion, and those things happens, and then we get the final stability of a electron, right? If you see the attractive interaction increase with the increase in positive charge, obviously, because if this is more, the attraction of proton and electron will be more. There is something called shielding effect of outside electrons for multi-electron atoms. So if you see the presence of electrons in the inner shells, if I have my nucleus, I have electrons here in 1s, then I have electron here in 2s, then p and e, right? So these electrons are there. These electrons creates a cells, or this electron screens the effect of this nucleus on these two electrons, right? The effect is lower due to the partial screening of the positive charge by the inner shell electron, and this is called shielding effect. This is called shielding of out shell electron by the inner shell electron. And the Z effect is the effective nuclear charge which this guy has on the nucleus, correct? But despite the shielding of outer electron by the inner electron, the attractive force experienced by this electrons increases with increase in nuclear charge, because this is more, right? This is more. This is, let's suppose 10, this becomes 20. There is a decrease. Let's suppose there's a 50% decrease, right? So there's a 50% decrease by the shielding. So instead of 10, it will experience, the outer shell will experience 5 in this case. Here, if you have put 20 here, the nuclear charge increases. The 50% screening, you still get 10. The effect is 10. So you can see here, in spite of screening, the effect is experienced, right? The attractive force increases with the increase in nuclear charge. Hope you understand this point. See, the screening is there. Let's assume the screening is effect is 50%. So whatever charge you get, this guy outer cell guy gets a 50% of that. So in this case 50% becomes 5, in this case it will become 10. So even if the screening is there, in this case, right, the effect is more, you increase the charge on the nucleus. And the energy of interaction between the nucleus and electron, that's the orbital energy, decrease nucleus and electron with the increase of atomic number. That is, if you take, let's suppose, one particular electron here, if you increase this number here for the nucleus, this nuclei will tightly hold this electron. So the electron energy will be all the more less, right? If you increase the number, atomic number here, there is a charge of the nucleus, this nucleus will hold less electrons all the more tightly, and thus the energy will be less. The shielding effect does not depend only on N, it depends on L also. I'll show you why. See, because all this attractive and repulsive interaction depends also on the shape of the orbitals, right? Example, if you see the spherical in shape, the s orbitals, they shield more because they get more chance, the electrons in the s shell get more chance to be near nucleus as compared to p orbitals, right? Because the shape is different, or d orbitals. So if it is s shell, it will shield the outer electrons all the more than p or d, correct? Right? And thus you can say that this Z effective, this shielding effect, or the effective Z experienced by the orbital decrease with increases azimuthal number, right? That is, s orbital will be more tightly bound to nucleus than p orbital, and p in turn will be more tightly bound to nucleus than d orbitals. So that Z effect experienced by the orbitals that decrease with increase in azimuthal quantum number, correct? The energy of s orbital will be lower. Why? Because it is more tightly held to electron. So it's very simple. If the nuclei is holding this electron more tightly, the energy of this electron will be less. It will have less freedom, right? So less energy it will have. So s orbital will held, the electron in the s orbital will be more tightly held to the nuclei because of the shape. So the energy in the s orbital will be less than the p orbitals. Hope you understand this. See, the electron is more tightly held to the nucleus, the energy of that electron will be less. For s orbital, this particular electron is more tightly held with s orbital, so the energy is less. Or you can say more negative actually, it will be more negative. So thus we have seen the energy of orbitals depends on N and L. And it was very complicated, right? Just now we have seen it depends on N, the shape of orbitals. So to make our life simple, we just have a thumb rule. The lower the value of N plus L, the lower is the energy. If two orbitals have same value of N plus L, the lower the value of N will take for the lower energy. It's a simple rule which we have given, but this rule is not 100% correct, but it works in most of the case. Because we don't want to deal into all the complexity in this class, it will be all too much for us to absorb now. So we'll just use this formula, N plus L, lower the value, lower is the energy. If there is a conflict, we'll take the one with lower value of N to have lower energy, right? And please note the energy of orbitals in the same subcells decrease with increase in atomic number. For example, if you see potassium, right, it has more protons. So this guy will hold electron all the more. Since it will hold electron all the more, the energy will be less. Hydrogen has less proton. It will hold the electron less. Since the electron is held a little in a weaker way, the electron will have higher energy. Hope you understand this. Since more proton, it will hold the electron more tightly. Since electron is held more tightly, the energy of electron is less. In this case, only one proton, it is loosely held this electron. Since the loosely held electron will have more energy. So for arranging the orbitals, we just follow the n plus L rule. 1s, 2p, 2p, 3s, 3p, 4s, 3d, like this, because you see this is n plus L rule. In this case, n is equal to 1, L is equal to 0, so 1 plus 0 is 1. Here n is equal to 2, L is equal to 0, 2. Here 2 plus 1, 3. Here 3 plus 1, 0, 3. But if you see, if you compare this 3, 3, this guy is 3, this guy is 2, so we'll take this guy as lower energy. 3p becomes 3 plus 1 is 4, 4s becomes 4 plus 0 is 4. Here also both are 4, so we'll compare these two. 3, this is n is 3, n is 4, so we'll take this as lower energy. And that's why we see this is all n plus L tree. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.